What is up, makers? My name's Jack Daly and welcome to the first episode of Makercanics. In this series we're going to be talking about everything you need to know about the mechanics. So let's start with the basics. The first couple of things that you need to know are mechanical advantage, velocity ratio and efficiency. So let's jump right in. So what is mechanical advantage? Well, there's mechanical advantage in three types of mechanisms, I guess. So you've got gears, levers, and pulleys. In gears, you generally have two types of gears. You have the driven and the follower. Now, obviously, the driven is the one that's powered by either a motor or something, and the follower is the one that's driven by the driven gear, if that makes sense. Let's say theoretically, obviously, gears work in teeth. So if you look at a gear and you've got them bumps, and we say, for example, the driven gear has 24 teeth and the follower gear has 18 teeth, then to work out the mechanical advantage, we would do the driver's teeth ratio, is what we call it, so that's 24, divided by 18, which is the follower's teeth gear ratio. And that obviously equals 1.3 recurring, but we'll say 1.34, okay? So now we have a unit, or a number, sorry. So now we can say that this gear mechanism has a mechanical advantage of 1.34. But what does that actually mean? What we're looking at is we're looking at a driver gear, which is a larger gear because it's 24 teeth, so that means it's larger, driving a smaller gear, 18 teeth, and then we have something called a speed multiplier. And that's the mechanical advantage. So obviously 1.34, I think we said that the mechanical advantage means that for every one time the driven gear goes round, the follower gear will go 1.3 rotations. Okay, so what is a speed multiplier? Well, a speed multiplier depends on obviously the gear ratio. So for example, for this one, we have the bigger gear driving the smaller gear, and this is a speed multiplier where the speed increases but the torque decreases, and all the torque is that's the force that the gear is going around with, but that's the rotational force. So then we have something on the opposite spectrum called a torque multiplier. And now this has got to do with when a smaller gear is the driver gear. So if we just swap these gears around, so the smaller gear is the driver gear, but the larger gear is the follower gear. Now once these turn, we're going to have something called a torque multiplier, where the torque of the gears, the torque of the follower gear increases, and the speed of the follower gear decreases. So that's called a torque multiplier. Okay, so let's talk mechanical advantage with levers. So obviously, if you've done any sort of like GCSE physics, you should know that regarding like the example that I'm going to use with a lever is the classic seesaw, where you have the seesaw here and then a pivot point. And now, mechanical advantage, the whole definition is to aim to let the machine do more. Obviously, mechanical is a machine, and then advantage is to obviously let the machine do more, and that's the advantage part. So what we aim, for example, with a lever, if we have a load of, for example, 10 kilograms on this side, we aim to put less effort into it, but still move the weight. And now, obviously, if we put a effort of 5 newtons in to move a load of 10 kilograms, then it's simply just 10 divided by 5, which is 2. Therefore, we have a mechanical advantage of 2. However, how do we actually achieve this in real life? Well, we all know the equation for moment. Moment equals force times distance. So therefore, if we want to decrease the force, we have to increase the distance. And now this is why you see sort of really long wrenches for like really big, massive bolts, and they'll stick the bolt, they'll do the wrench, and they'll start moving it here, and they've got really large distance for like a less force, because we have obviously a mechanical advantage. So next we have pulleys. Now we have two sort of different types of mechanical advantages in pulleys. Now one is where a closed loop, similar to gears. So we have a, say, larger pulley here called the driven or the driver pulley, and then we have the follower. So let's say we have a larger as a driver and a smaller as a follower for a pulley. And it's a closed loop, by the way, the rope goes round. It's simply if the diameter of the larger one is 10 and the diameter of the smaller one is 5, then we have a mechanical advantage of 10 divided by 5, which equals 2. Therefore, we have a mechanical advantage, and therefore we can sort of implement or slide in our speed and torque multipliers. So this one would be, if you said speed multiplier, you were correct. So obviously, because with big one driving a small one, and this is sort of a repeat of gears. However, with the next one, if you attach a pulley to the ceiling and have a load, and then you pull it, so if it's a 10 kilogram load, you're gonna have to pull it up with a 10 Newton force. And you're gonna have to obviously move it with the same distance. However, if you start adding more pulleys that the rope has to go through, it's the load divided by the amount of pulleys. So if we have a 200 kilogram load with it going through 4 pulleys, so you might have one here, one here, one here, and one maybe on the machine, and then it goes round all of them like that. I'll show an example somewhere. Once you pull it, not only gonna have to, you're gonna feel, the person pulling it is gonna feel a lot less because we have a mechanical advantage of 4. So for every 1 Newton of force put in, you times that by 4, and that's how much you're getting out. So if you so for example, in this case, you would have to put 50 Newtons of force in to move the 200 kilogram load. And that's mechanical advantage in pulleys. Okay, so next up we have velocity ratio. Now so next up we have velocity ratio. Now, in gear torque, this is pretty much the same as the mechanical advantage. It's to do with the distance of rotation. So if we have the driver gear here with 24 teeth, and we have the follower gear here with 18 teeth, we know that we have a mechanical advantage of 1.3 recurring. Now, to find out the velocity ratio, we do the same driver teeth divided by follower teeth, so that would equal the same thing. However, it's to do with the amount of distance moved. So the amount of distance moved of the driver gear, if it's moved 1 rotation, then the follower gear will move 1.3 rotations. Let's do this one more time. Oh. So that's velocity ratio for gears. So next up, we have obviously pulleys and levers. Now I'm going to go over these ones quite quickly because they're quite complicated. Obviously, velocity ratio, completely to do with the distance. So for example, in levers, if we obviously look at a seesaw again, if we have obviously the pivot point just wherever, we'll do it here for example, the velocity distance is calculated by, so if we have this as the initial position and this one as the final position, the distance from here to here is divided by the distance from here to here. And now if that's say 10, that one's say 5, and it's 10 divided by 5, meaning we have a velocity ratio of 2. Now with pulleys, this is a little bit different. It's sort of similar to mechanical advantage where we count the amount of pulleys used, but it's to do with the distance. So if we have, say, the pulley, you know, the one where you put it on the ceiling, if we have, say, 2 pulleys in there and we pull it by 10 centimeters, the load is only going to go up by 5 centimeters because the velocity ratio is 2, and therefore you do 10 centimeters divided by 2, and that equals 5. So in an enclosed pulley though, where you have a larger pulley here and a smaller pulley here, it's sort of the same as gears. It's to do with the amount of rotations. So if we've got a theoretical diameter of 10, theoretical diameter of 5, 10 divided by 5 equals 2. For every 1 rotation the driver pulley is going to do, the follower pulley is going to do 2. So that's sort of to do with the rotational distance. And last but not least, we have efficiency, which is really quite simple. I'm going to read you the definition. The definition of obviously efficiency in mechanical sort of terms is a measure of how much work or energy is conserved in a process. Now all the calculations we did in this video assume that it's 100% efficient. Now we know that's not true. For example, if we look at a lever on a pivot point, we know that there's going to be friction on that pivot point. Now, if I just got an equation for you. So we understand the output work divided by input work is obviously used to do efficiency. Now, most of these equations are to do with the output work divided by the input work being the same, therefore assuming 100% input work. However, so work equals force times distance, so 10 times 2 is the output work is 20 joules, right? So if we have a weight of 10 spaced away maybe 2 meters from the pivot point, that's work equals 10 times 2. That's how much work we need to do to get it to move. In an ideal world, the input work should be the same as the output work. However, due to friction, it's not. So, for example, if we have to put a force of 5 newtons down to obviously move this 10 weight, then we have to, obviously the distance is going to be 5 meters away. That's going to be 5 times 5, which is 25 joules. Now you can see we've got 25 joules to move a 20 joule weight, and you can see we've got 5 joules. And now that 5 joules is lost due to friction. Now this is obviously a terrible machine, but if we turn that into percentage wise, so 25 divided by 20 equals 0.8, and we obviously do that by 100, we then have an efficiency of 80%. Now what this means is 20% of the energy used is going to overcoming the friction, if that makes sense. So 20% of it is used. So if we look at 25 joules and 20, it takes 20 joules to move the thing up. However, we're putting in 25 joules, right? So that 25 minus 20 equals 5 joules. That 5 joules is used to overcome that initial sort of friction. And that's that. So those are the basic principles that you need to know for mechanics. I hoped you enjoyed this video. I sure did. Obviously, click here to subscribe to me. Click here or go to Instagram on here to sort of check out the guy behind the camera, Imaad, the guy who edited this. Thank you so much for editing this, by the way. Check him out on Instagram. He does awesome photos. If you want to check out this video, this is suggested by YouTube. It's what YouTube thinks you should watch, and I think you should watch it too. And then this video is a video I think you should watch because, yeah. So if you like this, subscribe. If you love this, like, and why not leave a comment if you have any questions. I'm always online, always ready to ask questions. Thank you so much for watching. Remember to keep making. Ah, that was so cringe. To keep doing. You do you, man.